Hello, welcome STT 315. This is recitation number 7. Today, this recitation will focus on 3 probability distributions, Poisson and hypergeometric and the normal distribution. So first, we're going to start off with Poisson distribution. So question 1 is, given that X is a random variable for which a Poisson probability distribution provides a good approximation, use statistical software to find the following. So you can either use R or use your calculator. But before I jump right into these questions, I just want to kind of recap what the Poisson probability distribution looks like. First we'll talk about the characteristics of a Poisson random variable. So this is from your textbook. So here are some characteristics. The experiment consists of counting the number of times a certain event occurs during a given unit of time or in a given area or volume, or weight, distance, or any other unit of measurement. So we're dealing with counting. The probability that an event occurs in a given unit of time, area, or volume is the same for all units. The number of events that occur in one unit of time, area, or volume is independent from the number that occur in any other mutually exclusive unit, and the mean or expected number of events in each unit is denoted by the Greek letter lambda. And here is what the probability distribution, mean, and variance for a Poisson random variable. So this top expression here is what we get for the probability distribution, which is P of X equals lambda to the X e to the negative lambda divided by X factorial. And remember, since we're dealing with counting numbers, X is 0, 1, 2, and so on and so forth. And our mu here equals lambda, and our sigma squared, our variance, equals lambda. And so lambda is the mean number of events during a given unit of time, area, volume, and E is our number E, which is 2.71828. Okay, so now just as a recap, this is stuff you should have learned in your lecture. Let's get into answering these questions for the Poisson probability distribution. So you can use R or your calculator to solve this. First, let's use R. So to find the probability that X is less than or equal to 2, where lambda equals 1, you're going to use this function, the p-poise, where you first enter your X and then you enter your lambda. So here our X is 2, because we have X is less than or equal to 2, so we have p-poise, and then 2, and then we have 1 as our lambda here. So if I go to R, you just can type this in, and you'll get 0.916986, which is what you get here. And also, if you wanted to recap using R, your different distributions, you can always write the question mark, and then if you're interested in the Poisson distribution, you can write question mark PPOIS, and that'll pull up a description. It'll pull up the different functions that the Poisson distribution has in R, the different arguments, like what your X is, your lambda, and then it also has details. So it has the PDF that the expectation and variance is lambda, and different facts about the Poisson distribution. So something that's helpful if you need a reminder when you're working in R, of the different properties of distributions. All right, and then if you want to use your calculator, you can use the function Poisson CDF and then lambda x. And so here our lambda is 1, which is same as before. And then our x is 2. So when you're using the calculator, the order of lambda x is different than when you use r, which is x lambda, but you'll get the same thing. And I have a TI Inspire calculator. So how you would kind of get this in your calculator, you would first hit menu, and then you would hit option 5, which is probability. Then you would hit option 5, distributions, and then option I, which is Poisson CDF, and then you would enter your input. So you would enter your lambda, and then you would enter your lower bound, which would be 0, and your upper bound, which is whatever your x is given. And so the lower bound would be 0 because remember, we're dealing with counting numbers, so x, you wouldn't have negative counting numbers. And also, the Poisson CDF looks something like this, which is just something helpful to keep in the back of your mind. So anyways, so part B, so we want to find the probability that x is less than or equal to 2, but now our lambda is equal to 2 instead of 1. So you would do the same function, except now we're going to change our lambda to 2. So if you do that in R, you would get 0.67667. So that's what you get, or you can also put it in your calculator like how I showed you before, and you'll get the same thing. And then here for the probability of x less than or equal to 2, but now our lambda is 3, you would, yes, you would put that into R as well. And I think I accidentally wrote the wrong order here. You would, for the calculator, it should be 3, 2. Because it should be lambda x, so that's my mistake for the calculator when you're inputting the values. But anyway, so the answer is 0.4232, and if you wanted to see it using R, you would just type in POIS23, and that will give you 0.4232. Okay. What happens to the probability of the event x less than or equal to 2 as this should be lambda, as lambda increases from 1 to 3? Is this intuitively reasonable? Okay, so this is why I wrote the CDF up here. So here we have the situation. So, you know, we in A, B, and C, we were interested in the probability of x less than or equal to 2, but here we have lambda equal 1, lambda equal 2, and lambda equal 3. And this is asking what happens when lambda increases. So if you notice, so when lambda equals 1, we get 0.9196. Then when lambda equals 2, we get something smaller, which is 0.6767. And then when lambda equals 3, we get something even smaller, which is 0.4232. So it decreases. And yes, I would say this is intuitively reasonable because as the mean increases, your probability of x less than or equal to 2 will decrease. And if I wanted to show this visually, so here, this isn't drawn perfectly to scale, but I'll kind of zoom in. Let's say this yellow is lambda, the CDF for lambda equal 1. This red is the CDF for lambda equal 2, and this blue is the CDF for lambda equals 3. If I were to plot, let's say this point here is 2. So like if I'm interested for x is less than or equal to 2, well, let's see what this probability is. So if you notice here, the yellow graph, that first one where lambda equals 1, is going to have that highest value. It's almost 1. And then when we have lambda equal 2, it's somewhere in the middle. We get I don't remember what it was, like 0.6767. And then when lambda equals 3, it's even smaller. It's 0.4232. So this isn't perfectly drawn to scale, but this kind of shows you what happens to the CDF as your lambda changes. So that's what this question was getting at. So as the mean increases, so as our lambda increases, so as it goes from yellow, red to blue, because our mean is lambda, our probability of x less than or equal to 2 decreases, and we can see that here. Okay. On to the next question. So applications of the Poisson distribution were discussed in the Journal of Case Research in Business and Economics. And I apologize for these stray marks. I couldn't get rid of them. In one case involving a hospital emergency room, 2 patients arrive on average every 10 minutes. Let X equal number of patients arriving at the emergency room in any 10-minute period. Assume that X has a Poisson distribution with mean 2. What is the probability that 4 patients arrive at the emergency room in the next 10 minutes? So here we're dealing with, our counting variable, and we're given to that it is a Poisson distribution. So, yeah, the question is, what is the probability that more than 4 patients arrive at the emergency room in the next 10 minutes? So we're interested in the probability that X is greater than or equal to 4 is what we're interested in. However, in order to solve this, we first need to solve the probability that X is less than or equal to 4 first in our calculator, because our calculators get this value. They always work from left to right on the graph. So that's why we need to get this value first, and then we can do 1 minus the probability of X less than or equal to 4 to get this. And this here is the complement rule that we had previously learned, where the probability of an event equals 1 minus the complement of that event. So anyway, so back to step 1. So to find the probability that X is less than or equal to 4, we can go to R and type in POIS 4, 2, where 2 is our lambda, because it was given that mean distribution with mean 2, and 4 is our X. So when we type that into R, we get, and it's already solved, but I'll just type that in to show you, you'll get 0.947347. But now we want to take 1 minus that, and then we'll get 0.0527. So that here is the probability that more than 4 patients arrive at the emergency room in the next 10 minutes. And if you wanted R to calculate that, to double check, you could do 1 minus the POIS 42, and you'll get the same answer that we got here, 0.05265. Okay. On to the next one, because I think, yeah, that concludes that. All right, so now we're on to the hypergeometric distribution, or yeah. So I think it would be easiest to just show you what the book says, just as a recap before we go into the problems. So, sorry, gotta find it. Here we go. So first, here are the characteristics of, so here we're still dealing with countable data. And so here are some characteristics of a hypergeometric random variable. So one is that the experiment consists of randomly drawing n elements without replacement from a set of n elements, r of which are s's for success and n minus r of which are f's, or for failures. And the hypergeometric random variable x is the number of s's or successes in the draw of n elements. And sorry, I don't know why my computer does that. What was the next page? Okay, here we go. So here's the probability distribution, the mean and the variance of the hypergeometric random variable. So we have P of x equals R choose x times n minus R choose n minus x, all divided by n, capital N choose small n. And the mean is mu equals n times R divided by n, and our variance is this long expression R times n minus R times n times capital N minus small n divided by capital N squared times capital N minus 1, where capital N is the total number of elements, R is the number of successes in the n elements, n is the number of elements drawn, and x is the number of successes drawn in the n elements. Okay, so now back to what we were working on. So given that x is a hypergeometric random variable with n equals 8, or capital N equals 8, lowercase n equals 4, and R equals 3, we want to display the probability distribution for x in tabular form. So here, this top row is going to be our x, and our bottom row is going to be the probability that x equals x. And so how you can do this is in R, you can use the d hyper function. And so here, the d hyper function works like this. So you'll put in your x. So like for this first entry here in the table, you would first put in your x. So in this situation, our x is 0. And then we have 3 as our R, which was given, 8 as our capital N, which is given, and 4 as our lowercase n, which was also given. And that'll give us 0.2121. And then you can go to R, and then you'll be changing this first value here to 1, but then the 384 will stay the same because that's what's given. That doesn't change because we're still in the same probability distribution. And then we have x equals 2 and then x equals 3. So to show you in R how I got these values right here. So I'm just going to copy and paste all of them, even though they show you right here. Okay, that's a lot to look at. Let me just do one at a time. So this is for where x equals 1. So we have d hyper 0.384. So that was our 0.2121. And then for our d hyper, but where x equals 1, we're going to get 0.509. And then for where x equals 2, we're going to change this value to 2 and run it again. And then we'll get, 0.2545. And then we're going to do where x is 3, which is 0.0242. And I believe, yeah, we only went up to 3. So, all right, so that's how I got those values here by using R. And now we want to find the mean and the variance. So if you remember, here's the mean and here's the variance. So we're given in our problem what n and R and capital N is. So we're just going to plug and chug basically. So for the mean, it's nr times capital N. So here our lowercase n was 4, our R was 3, and our capital N is 8. So that's 3 divided by 2. And then we have, and I don't know what that green stray mark is doing right there. And then sigma squared equals the equation I just showed you. So when you plug in what your R is and capital N and lowercase n, It simplifies to 3 times 5 times 4 times 4 divided by 8 squared times 7. And then that gives you 0.5357. And then another question that I would like to ask, but that's not on this sheet, is what if I asked you to find the probability that x is less than or equal to 2? So that is the same thing as 1 minus the complement of that, which is the probability that x is greater than 2. So we have 1 minus, so in this situation, we just have the only option that's greater than 2 is 3, where x equals 3. So we can do 1 minus the probability that x equals 3, which is 0.0242. So when you do 1 minus that, you get 0.9758. And so here that gives us the probability that x is less than or equal to 2. And this isn't drawn to scale, I'm just realizing now. And then you could also do this in R by doing P hyper, and you would put 2 here and then 384. All right, so now, and I'm not sure too if I remembered. Oh, and then also, like I said, if you wanted a refresher of the distribution, the probability distributions and the different functions in R, you can do question mark D hyper into your console, and it'll give you your different usages. So here you have D hyper, which we used in the first part of the question, or P hyper, which was the last part that we just talked about. So here we have, for D hyper, we have our X, and for P hyper, we would put in the quantile. Okay, so now question 4. The Journal of Behavioral Decision Making published a study of how guilty feelings impact on the job decisions. In one experiment, 57 participants were assigned to a guilty state through reading / writing task. Immediately after the task, the participants were presented with a decision problem where the stated option had predominantly negative features. For example, spending money on repairing a very old car. Of these 57 participants, 45 chose the stated option. Suppose 10 of the 57 guilty state participants are selected at random. Define X as the number in the sample of 10 who chose the stated option. And our first question is we're going to find the probability that X equals 5. So here we're going to use the D hyper function, and our X is 5, which we get here in the question. And then we have our R is 45, which remember that R is the number of successes in n elements. So we have that 45 chose the stated option. So if you chose the stated option, that's seen as a success. And then 57 is our n, so that's our total participants. But then our small n is 10 because we have 10 of the 57 participants were selected at random. So that's like our smaller sample within the larger population, if you want to think of it kind of like that. So you put that into R right here, and it gives you 0.2401609. So that is the probability that X equals 5. And remember, X is the number in the sample of 10 who chose the stated option. So that the probability that 5 in the sample of 10 chose the stated option is like 24%. Okay. Now we want to find the expected value of x. So we're still dealing with the same equation of n times r divided by capital N. So n is 10, or our small n is 10, our r is 45, and our capital N is 57. So plug and chug, and then you get 7.8947 as the expected value of x. Okay, now we're dealing with a uniform probability distribution. So suppose that x is a random variable best described by a uniform probability distribution with c equal 20 and d equal 45. So we want to find f of x. So for the uniform probability distribution, we have, so for x in between c and d, so our c here is 20 and our d is 45. So we have that x lies in 20 to 45. And so our f of x for a uniform distribution is 1 divided by d minus c. So in this situation, it would be 1 divided by 45 minus 20, which is 1 over 25. So if I wanted to just graph that, our density would look like this. So we would have here on our x-axis, I have 20 and 45. So this is our c and this is our d. And our height is 1 over 25, or 1 over d minus c. And so we have that x is 0, but then in this interval here, it's 1 over 25, but then elsewhere x is 0. Or sorry, not x is 0, our f of x is 0. All right, so now we have to find the mean and the standard deviation of x, given that it's a uniform probability distribution. So for the mean for a uniform probability distribution is c plus d divided by 2. So we would have 45 plus 20 divided by 2, which is 32.5. So that's our mean for this uniform probability distribution. And then our variance is d minus c squared over 12. So that's for any uniform distribution. So now we're gonna, we need to find what the standard deviation is. So we're gonna take the square root of our variance. So if we take the square root of this, it'll equal d minus c, because the square root will get rid of the square. But then we have this over the square root of 12. So now if we plug and chug for the values that we were given in this question, we can do 45 minus 20 divided by the square root of 12. And that will give us our standard deviation of 7.2169. Now we have to find the probability that x lies between 20 and 30. So we have the probability of a less than or equal to x less than or equal to b equals b minus a divided by d minus c. If c is less than or equal to a, which is less than b, which is less than or equal to d. And notice here that this is a strictly less than, so that way we don't get if there was an equality in here as well, then we would get 0 as our numerator. But anyways, okay, so let's just plug in what we know. So here are, a equals 20 and b equals 30. So our numerator is 30 minus 20 divided by 45 minus 20. So if you simplify that, you get 2 divided by 5. And to find the probability that x is greater than or equal to 45, that's going to be 0 because X lies in in the interval CD. And so if we have X greater than or equal to 45, it's going to be 0. And if we wanted to look at our graph here of f of X, you can see that as well. If X is greater than 45, so that would be this red line on the x-axis past 45, our f of X for those X's are 0. So, which is what we get here. But that's a way to visualize that. Okay, next is question 6. So we're dealing with standard normal random variable. So here as a recap, our probability density function for a normal random variable is 1 divided by sigma over 1 over sigma times the square root of 2 pi times e to the negative half times x minus mu over sigma all squared. So where mu is our mean of the normal random variable x, sigma is our standard deviation, and then pi and e are the numbers, pi and e. And then the probability that x is less than a is obtained from the table of normal probabilities or using statistics software, so we can use our calculators. And then for standard normal, this is our probability distribution is given by this, and our standard normal distribution has our mean 0 and standard deviation of 1. And usually we denote a standard normal distribution by z. Okay, so that's just a recap of normal distribution. So in this problem that we're working on right now, we're dealing with the standard normal distribution. So we have our mean 0 and standard deviation as 1. So find the following probabilities for the standard normal variable z. So here it's asking for probabilities. So a way I like to think about it is we're looking for, okay, what is the area under the curve? And here this also means that just z is a standard normal, so normal distribution with mean 0 and standard deviation 1. Anyway, so we're first given, or we want to find that the probability that z lies in the interval -1 to 1, close bracket. So we have we can do normal CDF in our calculator, -1 to 1, and then our mean is 0 and our standard deviation is 1 because we're in the standard normal setting. And if we put that into our calculator, we'll get 0.683. So if I wanted to represent this on a graph, let's say this is our standard normal distribution, and here we have our mean of 0. So we want to find the probability that that z is in -1 to 1. So that's this interval here. So what is the area under the curve here? So the area under the curve here is 0.683. So for the second part, so part B, we want to find the probability that z is in the interval -2.16 to 0.55. So if I were to represent this on the graph, we would have, let's say, so our mean is still 0 because we're in standard normal, and we have, let's say this is -2.16, and this vertical line is 0.55. We want to know what is the area under the curve. So we're going to use normal CDF function, and so our lower bound is -2.16. Our upper bound is 0.55. Our mean is 0. Our standard deviation is 1. So we'll get 0.693. So that's that area under the curve. That's that probability. Now next is the probability that z is greater than or equal to negative 2.33. So if I were to represent this on a graph, here our mean is still 0, and negative 2.33 is somewhere over here. And I'm interested in the probability that z is greater than that value. So what is the area under the curve of this point onward? So my lower bound is going to be negative 2.33. My upper bound is going to be infinity because we want the area under the graph starting here, but then, everywhere to the right of that. So a way to just kind of write infinity in your calculator is 10 to the 10, even though that's not infinity itself, but as you keep following this, the area, the line will be, okay, sorry, I'm like tripping over my words. The graph will get, sorry, the probability density function will get really, really close to 0, even though it won't touch. But anyway, so you can just use 10 to the 10 to mean infinity. So that's our upper bound, and then we have 0 as our mean, and our standard deviation is 1. So that's 0.99. So that's that area under the graph. That's shaded. And then the probability that z is less than or equal to 1.33. So that's going to look like something like this. So 1.33 is over here, and we're interested in the area under the graph, the area that's shaded. So we have our lower bound is negative infinity, so negative 10 to the 10. And then we have our upper bound as 1.33, and then mean 0, standard deviation 1, and then we'll get 0.908. Question 7, we want to find a value of the standard normal random variable z. We'll call it z0 such that, and then we have these questions. So now we want to find the specific value on the x-axis. Before we were finding probabilities, which is the area under the curve, but now we want to find specific values, the specific z0. So here we're given that the probability that z greater than z naught equals 0.05. So if I were to represent this on the graph, I would have, so we're still in a standard normal random variable setting. So our mean is 0. And our z naught is going to be somewhere over here because greater than that z naught value, we're given that the area under the curve is 0.05. So we need to find what is this exact value. However, the way the calculator works is to find this value, it kind of works from left to right. So you want to input the area under the curve up to that value. So we kind of have to do the trick that I mentioned before, where you're going to do 1 minus the complement. So we have 1, okay, so we can do 1 minus the probability that z is less than or equal to z naught is 0.05. So that means the probability that z is less than or equal to z naught is 0.95. So now when we use the inverse norm function, since it works from left to right, we're going to do 0.95, and then our mean is 0, our standard deviation is 1 to get 1.64. So that means this value here is 1.64, our z naught. Okay, let's try another one. So the probability that z is less than or equal to z naught is 0.025. So here, if I'm going to write my graph, I first draw my green histogram. I have 0 as the mean, and I'm given that the probability that z is less than z naught is going to be 0.025. So the area under the curve is 0.025 to the left of z0. And so now I want to find, okay, what is this specific Z0 value? So I'm going to use the inverse norm function. And because the calculator goes from left to right, here I don't have to use the same trick because I'm already given that area under the curve up to that Z naught point. So I have inverse norm 0.025, and then mean 0, standard deviation 1, and that'll give us negative 1.96. So that's that specific value here. So this little tick mark is the value negative 0.96, which I would expect it to be negative, because we're to the left of 0. Anyways, next one is the probability that Z is greater than Z naught equals 0.1. So here we have, if I were to draw my graph, I would first draw the green histogram, and then I have, our green density, keep saying histogram, density, and then we have this Z naught we don't know, but we are given that the area under the curve to the right of this is 0.1. So if I do 1 minus 0.1, I'll get the area under the remaining portion of the curve, which is to the left of Z naught, so that's 0.9. And so since our calculator works from left to right, we're going to use inverse norm of 0.9 and then 0 and 1, which gives us 1.28. So this little strict tick mark is at 1.28. Okay, next, suppose that X, one last thing to kind of recap this page. So here we are finding probabilities, which is the area under the curve. So we use normal CDF function, where here we were finding the specific value on the x-axis, on the x-axis, and we would have, we would use inverse norm function. All right, so question 8. Suppose X is a normally distributed random variable, but now our mean is 50 and our standard deviation is 3. So we're no longer in the standard normal. We're just in a normal distributed random variable. And we want to find a value of the random variable, call it x0, such that, so we want to find again that specific value on the x-axis. So in this one, we're given that the probability that X is less than or equal to X0 is 0.8413. So here, if I were to draw my histogram or my density, I have that my mean is now 50. So this bell-shaped curve is centered around 50. And then the area under the curve up to X0 is 0.8413. And so I'm going to use the inverse norm function. And so we are working from left to right. So I don't have to do the trick that I mentioned before because we're given this area to the left of the point we're interested in. So we can do inverse norm 0.8413, but our mean now is 50 and our standard deviation is 3. So when you put that in your calculator, you should get 52.999. All right, as our x0. The next one is the probability that 41 is less than or equal to x, which is less than x naught, which equals 0.8630. So there's 2 steps to this. And I drew my picture at the bottom of this page, the picture that corresponds to B. So my first step in figuring this out is I always draw a picture, and so I would draw our density. So that's the green line with 50. It's centered around 50, and so the probability that 41 is less than or equal to x is less than x naught equals the probability that x is less than x naught minus the probability that x is less than or equal to 41. So in other words, we're given first that, so let's say we have 41 here and our x naught over here. We're first given that the area under the curve between these points is 0.8630. This is what we're given. And the goal of this is we want to find this x0. So our in-between step is this red step. We got to find the area under the curve here. So that way we can have this total area under the curve up to x naught and put that into our calculator to find what that specific value of x naught is. So we would have the probability that x is less than or equal to 41, which is this area under the curve, is going to be normal CDF. And our lower bound, well, first of all, it's normal CDF because we're interested in the area under the curve. And our lower bound is going to be negative infinity because we're starting from way out here. And then our upper bound is going to be 41. And then our mean is 50 and our standard deviation is 3. And that gives us 0.00135. So that's that area here under the curve. So now we have this area under the curve and we have this, which we were originally given. So if we add those two together, we get the probability that x is less than or equal to x naught, or sorry, is less than x naught as 0.86435. So you just add those two numbers together to get this. So now we're finally ready to use this function in our calculator because we have the area under the curve up to this point is 0.86435, and then we have our mean as 50 and our standard deviation as 3, and then that gives us 53.3. So that's our x naught. So there were two steps to that problem. All right, and then the last problem is part C. So 1% of the values of x are greater than x naught. So first, what I would do is I would draw my density function again, and I have it centered around 50 because we're still in the same situation where mean is 50 and our standard deviation is 3. And we have, so we were given 1% of the values of x are greater than x naught. So here, if we have x naught over here, we have 1% of the values are greater than x naught. So that's the area under the curve. So that would be 0.01 is the area under the curve. But to find this x naught, our calculator works from left to right. So we need to use this area under the curve. So first we got to find that, and then we can use our inverse norm function. So the probability, so to recap, the probability that x is greater than x naught is 0.01. So the probability that x is less than or equal to x naught would be 1 minus this probability. So 1 minus 0.01 is 0.99. So we'll use that when we use the inverse norm function in our calculator, and then we have our mean as 50 and our standard deviation as 3. So when you put that in your calculator, you should get that x naught is 56.98. And that concludes today's recitation. I hope this was helpful.